Hi, I'm Russ Baker. This segment is about parametric equations. Usually when we select ordered pairs, we do it by selecting values for x and then use a formula to find values for y. But there's an alternate way we could do that as well. We could choose a third variable, which we call a parameter, and have formulas for both x and y. Let's look at the definition of parametrics. Parametric equations of a plane curve. A plane curve is a set of points x, y, such that x is some function of t and y is another function of t, where both f and g are defined on some interval I. The equations are the parametric equations, and the parameter is called t. Your graphing calculator can do parametric equations if we make a few alterations. Let's do that now. We'll turn the calculator on, push the mode key. 4 rows down, you'll see that the calculator has highlighted function. We move over to PAR for parametrics and hit enter. What will happen now is that if you push the window, you'll see some different items that you haven't seen before with t's. If you push the y equals, you'll see slightly different as well. I've already entered our first equation set of parametric equations into this calculator. Let's take a look at them and talk about the interval for a second. We want to graph the parametric equations x equal t plus 2 and y equals negative 1/2 times the square root of 9 minus t squared. We should always identify some variables that will allow t to take on different values. We want our t in this case to be on the interval -3, 3. Now let's go back to our calculator and see what the graphs will look like. We know that we have the equations already typed into the y equals menu. Let's take a look at the menu for a minute. Our t minimum, we said we wanted to be -3. Our maximum we wanted to be +3. We can leave the step alone. The remaining x max and minimums and y minimum and maximum are the same as the standard screen. Let's see what happens when we graph this particular function. This parametric graph looks a bit like the lower half of an ellipse. Now, one of the things that we'll need to do is, given a parametric equation system, we'll want to substitute and try to find the equivalent rectangular form. Let's take those two parametric equations and try to find its standard rectangular form now. Here we go. We'll look at the simpler one first and solve this for t. So t equals x minus 2. Now we're going to take the x minus 2 and substitute in the y version. Y equals -1/2 times the square root of 9 minus x minus 2 squared. Now technically we're done because we have an equation in rectangular form. There's a y and there's an x. But this doesn't look much like an ellipse or anything else we recognize for that matter. So let's continue manipulating the equation a bit. Let's multiply both sides by 2. There we go. And now let's square both sides. The square root sign will fall out of the problem. Let's add the x minus 2 squared to both sides. And finally, we'll divide both sides by 9, leaving us with 4y squared over 9 plus x minus 2 squared over 9 equals 1. This is a more recognizable form of an ellipse. The real question is, why did our graph of our parametric equations not turn out to be a complete ellipse? why was it only the lower half? The answer to that question lies all the way back up at our defining equation in parametric form of y. The negative sign implies here that this is negative 1/2 times the square root, and the square root is in fact a positive number. So the y values were restricted here to being only negatives. Hence we got the lower half of the ellipse instead of the entire thing. Now here's one for you to try. Find an equivalent rectangular equation of these parametric equations. Stop the tape to do your work and turn it back on to find the solution. Let's see how you did. The first thing we want to do is change the x equals t plus 2 and solve it for t. Just as before, we get t equals x minus 2. Now we'll make that substitution into the y parametric, 1 over x minus 2 plus 2, which is y equals 1 over x. Is that what you got? I hope so. Let's see what happens when we try to graph these parametrics in our calculator. We're going to leave the first one the same, and we'll change the second one to 1. Well, we'll clear that first. 1 divided by parentheses t plus 2. Now we have to look at our intervals again, so we'll go to the window, and we're going to put in negative 10 to positive 10. Don't use zoom 6 when you're doing parametrics, because it's the zoom 6 option for parametrics is designed to be used with trigonometry, not with the algebraic versions that we're using here. Let's see what it looks like. This is the graph of a hyperbola, and that's what the graph of y equals 1 over x happens to be. So it's just what we would expect it to be. If we can turn parametric equations into standard rectangular form, we should be able to do the reverse of that. We should be able to find an equivalent set of parametrics for any rectangular form. Let's take a look at an example. If we want to find an equivalent set of parametric equations for y equals the square root of 3x plus 2, we have only to consider how the function originally was formed itself. By the way, the parametric forms are not unique. There could be several different versions to this answer. Let's see now. One thing we could do is say, let t be the radicand, that value underneath the radical, 3x plus 2. Solving that for x, we'd get t minus 2 equals 3x, and x equals t minus 2 over 3. There's our first parametric equation. Our second one is to go back and say, well, what would the y parametric have to be? Well, if 3x plus 2 is going to be our t, then the second parametric is just y equals the square root of t. Now let's check the interval of t and see what would be appropriate. We know from the beginning that x is in the interval negative 2/3 to infinity inclusive. That means that x is greater than or equal to negative 2/3. But x is t minus 2 over 3. We'll substitute. With two fractions in an inequality with the same denominator, we'll just write t minus 2 larger than or equal to negative 2, add 2 to both sides, and we should use t any t larger than or equal to 0. And so the interval over which we could consider our t, our parameter, is 0 inclusive to infinity. There are some fascinating and interesting applications dealing with parametrics. We'll just consider one for now. Let's look at a projectile problem. A projectile is fired with an initial velocity of 400 feet per second at an angle of 45 degrees with a horizontal. Find each of the following. We'd like to know when the projectile strikes the ground, its range, that is, this isn't the range of a function, it's the downrange or horizontal distance traveled by the projectile, and third, the maximum altitude. The parametric equations for a projectile fired at an angle of 45 degrees are found in your textbook. Here they are. X is v sub 0, the initial velocity, times the square root of 2 over 2, t. Y is the initial velocity v sub 0 times the square root of 2 over 2t minus 16t squared. Our problem suggests that v sub 0 is equal to 400. Well, then we can find out what x is, or we can find out what y is. Our first part of the problem says, let's find out what y, when y is 0, because that's when the projectile will hit the ground, when y is 0. Let's see what this equation looks like with v sub 0 substituted in. 400 times the square root of 2 over 2t minus 16t squared. Remember now, we want to know when the projectile hits the ground, so y is 0, and we'll look at this equation. We could reduce this and just write 200 radical 2t minus 16t squared. Well, we can factor this as well and get 0 equals t times 200 radical 2 minus 16t. We see from this that t can have two values. T equals 0. That's not too surprising. The projectile is on the ground when it's fired. The second value is 200 times the square root of 2 over 16, which, when you do the calculation on that, turns out to be about 17.7 seconds. We therefore now know that at time 17.7 seconds, the projectile will hit the ground. The second part of our problem asks us to find out how far away the projectile will strike the ground, and for that we need our x formula. 400 times the square root of 2 over 2, t, x equals 200 radical 2 t. And, well, what t do we want to use? Well, we know that it hits the ground at 17.7 seconds, so we better use that. 200 times the square root of 2 times 17.7 seconds comes out to be approximately 5,000 feet from its initial firing point. Our third problem is to find the maximum altitude. Now, the maximum altitude, because we know that a projectile travels in a parabolic path, will happen at exactly halfway through the flight. That means that t, for the maximum, will occur at 17.7 divided by 2, or about 8.85 seconds. We're going to therefore go back to the y parametric equation and substitute that value in. Y equals 400 square root of 2 over 2 times 8.85 minus 16 times 8.85 squared. When we calculate that arithmetic using our calculator, we'll find that our maximum altitude is approximately 1,250 feet in the air, occurring at time 8.85 seconds. Parametric equations add a whole new dimension to using algebra and your graphing calculator. Practice altering equations both into parametric form and from rectangle into parametric form and back again until you can do it with ease. Also experiment with your calculator with different intervals to see how it can change the graph. Practice, they're fun.